Hello, my name is Gary Swiney, and this is homework 3 for machine learning. So we have a couple of responsibilities in this one. We're going to check out different classification methods, KNN, multimodal native Bayes, random forest, gradient boosted. And in this we're going to apply a couple different things. First, we're going to use for cross-fold validation and identify the parameters for each classification that's the best. Then we're going to use different types of data normalization to find out if that can boost performance. And then we're going to compare the accuracy to the testing data set. And then we are going to inspect what features are important, if we can, and also any samples that are misclassified. And then we're going to determine the best algorithm overall. So this starts with KNN. First thing we had to do is I had to write a little program that would go through our CSV and create headers or feature number labels for each entry in the Excel sheet. It was just the easiest way for me that I create my own little column with a feature name that's essentially a number because it's 1,000 by 25,000 matrix. The X variable is, and not the true or false labels. So it's pretty big and it was unlabeled, so I wanted to label it first. And I also have an optional thing here to enter the Y tables as a 1D matrix. So here are our scalars we're running with for k nearest neighbors, which is standard scalar, min-max scalar, or no normalization. These are 3 different types of data normalization, including no normalization. So we run this little loop that for each scalar name will fit transform, and then we will test our parameters. So for k nearest neighbor, it's our neighbors, and I chose some multiples of 2 here to train it. We have our cross validation of 4 here, and then we're going to add it to a nice little plot in order to analyze it. And we can look at all our results here, and we see that our best result is somewhere right here, KNN 16 with no normalization, and it's also the same as k equal to 16 with min-max scalar. So as you can see here, the graph, we see the same thing. Min-max scalar and no normalization is actually overlapping on this green, so you can't see it behind it here. And standard scalar performed the worst here. So we see our peak is here at k equal to 16, which we measured. So we throw that in for our test, and we also use min-max scalar as our optimal scalar or our optimal normalization. And now we test the different distance matrix. This is only to reduce testing times, is separating it like this. So we test Euclidean, Manhattan, Minkowski, Chebyshev, and cosine. And after we tested all of this, it ended up that cosine had the greatest results here, and as you can see in the graph plotted here. So we can determine that for k nearest neighbor, the best fit was at nearest neighbor 16, with min-max worked fine, and the distance metric of cosine was our best fit. So now we can calculate the accuracy against our best fit on the testing data to get a testing accuracy, and our test accuracy was 0.762 against our training accuracy, which is 0.761. So we actually tested very good. The training data was not that great, but in terms of score, 0.76 is, okay, so bad. But our test accuracy is 0.762. So you know what? I would say that ended up being pretty good at our point of best fit without being too overfit or underfit. So next on the list that we had to check was multimodal, multinomial naive Bayes. So for this, I switched up the scalars we chose so that all values could be between 0 and 1, or at least positive, so we're not passing off negative numbers. So I changed to max absolute scalar. Then we're testing alpha values here, a couple of handpicked ones. So we do sort of the same thing for each type of scalar. We're testing another scalar, and all this is going to spit out into a nice little graph. where we can compare against all our parameters. And again, if you pay attention here, you'll see that no scalar performs the same as max absolute scalar. So, and min-max scalar performs the worst out of all of them. Just to double check. Yes. So, comparing the results of those, we can see them here. And so we choose, even though max absolute and no scalar have the same results, we choose max absolute scalar as our best normalization method. Just to pick one. And so our test accuracy with max absolute value is 0.8324 at alpha of 0.1, so 0.8324 against our training of 0.83244. We see right here. So again, we're testing pretty good at our point of best fit. You can't expect, test much better than that for how well it is. So I would say this is our best model by far, is our multinomial in B. And here we can see some features that were misclassified, that failed. We see 4, 5, 8, 17, 25, and this will change as we go through models, but these are features that are misclassified or weren't that helpful. Now we are going to the next portion, which is random forest. So as we go through random forest, we're doing the same thing, changing our in estimators, which is our trees, our max features, which is square root of n or log of 2 of n, and then max leaf nodes. I chose 10, 20, and 50. So we're, again, trying all those against a cross-validation fourfold, and we're putting that into a plot, and we're comparing them, and we're grabbing the best one, and then we're doing our feature importance. So here we could see all the different possibilities. This one I wanted to be all-inclusive in calculation since it didn't take that long for each one. And so if we go through all our calculations, you can kind of see at the end here, this is looking like our best score, which is 200 trees, log 2 of n, max features, and max leaf nodes of 50. And if you look here, actually, all three of them for the normalization methods line up exactly on this graph. So all three performed exactly the same at each point. But regardless, the highest point was all the way over here. In the top right, you can see as our index goes up, meaning that we're choosing these greater numbers, which is our in estimators equal to 200, log 2 of n, max features, max leaf nodes of 50, and that tested at 0.82552 against this 0.8262. Again, that's really, really close. Not quite as good as our naive Bayes, but still pretty good in general. Here we can see our top 10 features of importance. This rates their index, and because there's 1,000 features, it's easier to just look at the top 10. We could see them in order. Here is the most important features, and then we have our misclassified features, which change a little bit here: 2, 3, 8, 17, and 26. Those are a little bit different than we saw in the naive Bayes. And then last but not least was our gradient boosted. Gradient boosted by far took the longest to run for me. I'm not sure why, but again, we're choosing our scalars. And I chose in estimators of 100, learning rate of 0.1, and max depth of 3. This is the general form, and also it performed the best for me, and it took the least amount of time to run. All the others took a way, way, way too long to run when I was variating parameters. So you can see here I keyboard interrupted because it was taking so gosh darn long. But I saw that min-max scalar and no scalar performed the same, so I chose no scalar to test the fit against. So I wrote up the code here to evaluate the test score and compare it, and then find the top 10 features again, and then find the misclassified samples. So my test accuracy at the same parameters was 0.81228, which was against the training score of 0.809. So again, we're testing pretty good, but not quite as good as the naive Bayes. Our top 10 features of importance here, a little bit different than we saw with Forest, And then our misclassified samples, again, a little bit different, 3, 6, 8, 13, and 7. All of these misclassified samples. And that concludes the analysis of this homework, and Naive Bayes was found to perform the best out of all of them. Thank you.